Okay, so in this lesson, we're going to look at some tangent line problems. The first one is a tangent line approximation. So before we do that, we're going to start reviewing real quickly tangent lines. So remember, a tangent line touches a curve at one point and shares the slope of the curve at that point. Given a point on the curve, a, f of a, and the derivative at that point, f prime of a, we can write the equation of a line tangent at a. Okay, so the tangent line's right here. What is that equation going to be? I need a point and a slope. And this right here is just the point slope formula in our calculus format. This is the y value. This is the slope at that point, x minus a. You can also move that over in the format like this. I can write it as y equals f of a plus f prime of a times x minus a. And I'll most likely write it in this fashion right here. But either one is fine. We can use a tangent line to approximate the value of a function at a particular point near a. Okay, so let's say for the sake of argument, I don't know what this function equation is, but I do know the tangent line equation at a. Well, then I can use that tangent line equation to approximate values very, very close to a. So if I'm really close to a, but not on a, I can use the tangent line equation to give me an approximate value that's really close to the actual value. And that's what this is about. How do I use tangent line approximations? Okay, so let's take a look at some examples and show you how this can be done. So here is our first example. Let me zoom out just a bit so you can see the whole question. I have a function f of x, the square root of x plus 1. I want to find the linearization of f. And what that means is simply this. You're going to find the tangent line there at 0. You're going to find that tangent line here at 0. The linearization means this. Any function that I have, if I zoom in close enough, if I zoom in really, really close to 0, what's going to happen is this curve is going to take on the aspect of this line. So it becomes a linear, it looks linear. That's because it's called the linearization of this function. You're going to zoom in extremely close. And so every function looks like a line if you zoom in close enough. All right. So first thing we have to do is we have to use this tangent line equation to help us approximate this value. Okay. So to do that, I need a point and a slope. I got to find the line equation of the tangent line at 0 right there. And so to do that, I need to have a point and a slope. So I need to find the value of the function at 0, which would be 0 plus 1, which is 1. And I have to find the derivative at 0, which I don't know yet because I have to find the derivative. So we take this equation of f over here. This is x plus 1 to the 1/2. We find its derivative, x plus 1 to the negative 1/2. And if you wanted to rewrite this, you can write it as 1 over 2, and then the square root of x plus 1. This is the same thing. And then I want to plug in 0. So if I plug in 0 in here, I'll get the square root of 1 again, and then this just becomes 1/2. So once I have that, I can write my tangent line equation, which is y equals the value of the function at 0 plus the slope times x minus 0. Okay? So I wrote it like that so you can see it all, and then you can clean this up to be simply 1 plus x over 2. So this is my tangent line. Now, let's go here because we wanted to find this approximation right here. To do that, I need to use this right here. So what does the x value have to be to get that quantity? So what does x have to be to get that quantity? Okay, so x has to be 0.02. So I need to find f at 0.02. This then will give me the square root of 1.02, which is what I'm trying to approximate. And I can use the tangent line. Make sure you put approximations here because these are not equal. And plug in that number into this, so I get 1 plus 0.02 over 2, which gives me 1.01. That's my approximation. Okay, and that's what we were asked to do. Find an approximation for using the tangent line for that quantity, and there it is. If you use your calculator and type this in, you're still going to get an approximate value, but here's what you get off the calculator. You're going to get 1.00995049. So you can see that that's a pretty good approximation for the actual. Here's another look at the same type of problem. A function is differentiable. It's known that g of 2 is 7, g prime of 2 is -3. Use the tangent line approximation at x equals 2 to estimate t at 2.1. So I need to find a point and a slope, and they actually gave me all of those. The point is right here, 2, 7. The slope is -3. So I can go right to my tangent line here. So my tangent line can be y equals the y value at 2 plus the slope times x minus 2, which is the point we're trying to go towards. So this is my tangent line equation right here. And then I can use that to approximate g at 2.1. So this becomes 7. Excuse me, I should put an approximation here. Do not put an equals. Approximately 7 minus 3 times 2.1 minus 2. So if I take this right here and I work this out, and I'm going to get a value of 6.7. So that would be my approximation, given that information. I can also have information given in this fashion, where I gave you information in a table. Okay, so you look at the question, you read it, select the values of a differentiable function f and its derivative, f prime, are given in the table. Okay, write an equation of the line tangent. As soon as you see those words, you know you need a point and you need a slope. Okay, at 4. So 4 is the magic number right here. We're going to use this equation to approximate this. So the first step is to find the tangent line. I need a point and a slope at x equals 4. So at x equals 4, what do I have? So what is the y value at 4? -5. What is the slope at 4? 6. And then x minus 4. This is my tangent line at that point. Now I want to approximate that. So I simply, f of 3.8, okay, is approximately -5 plus 6 times 3.8 minus 4. Okay, and so then you work this out, and you should get a number that's 6.2. Okay, and that's my approximation. Let's continue this process here, and let's talk about something a little bit different, another take on the same process of these problems. I need to flip this over here and show you one more thing. We're going to be talking about it in more detail in the next unit, but here's a little precursor of what's coming. Use the slopes and the curvature of a graph to determine if the tangent line approximation is an overestimate or an underestimate. And what they mean by that is this. If the slopes are decreasing, so that means the tangent line it's going to be above the curve. See this? So that means the tangent line approximations are going to be an overestimate. They talk about the curvature, and that means concave up and down. When it opens like this downward, see how the bump is above and it opens downward? This is called concave down. If it opens upward like this part right here, that would be concave up. It's opening up. So that's the two ones we're going to talk about this in more detail in the next unit. But we can use this concept into this visualization to help us understand that if I have a curvature going up like this, then the tangent line is below the curve. indicating that we're going to have an underestimate. So let me show you how this works. And by the way, the concave up and down is associated with the second derivative. So let's go take a look at an example to show you how this works. Okay, so here's our problem. For a differentiable function f, it is known that f at -2 is 5, f prime at -2 is -3, and f double prime at -2 is -5. And this part right here is going to help us with the curvature. All right. So first part here is find a tangent line to estimate a -2.1. So we've done that several times already. So here's our part A. We need our equation of our tangent line. So I need our point, which is 5, our slope, which is -3, and then x minus a -2. So that is my tangent line right here. This is my tangent line. And then I want to use this to approximate f of a -2.1. So we just plug in a -2.1 in there. So you're going to get 5 minus 3 times -2.1 plus 2. And if you work this whole thing out and combine numbers and all that kind of stuff, you're going to get the value, hopefully, of 5.3. Okay? So that is my approximation. So the next part here, part B, is this approximation going to be an overestimate or an underestimate of the actual value of the function at -2.1? And what is my reasoning? Okay? So that is determined by that right there. Because this second derivative deals with the curvature, the concave up or concave down nature, and we see that it is negative, then that means it is concave down. And since it goes like this, the tangent line's up here, we can see that we're going to have an overestimate. So part B you would write it this way. The approximation is an overestimate because, always got to tell me why, f double prime at -2 is less than 0. What you're saying here is you're saying that it's negative. And this means the graph of f of x is concave down at x equals 2. And that is your reason behind how I know it's an overestimate. Okay? The second half that we use tangent lines for is in these problems down here. The first one was for estimating. This one is actually for finding tangent line equations and various ways of doing it. So I got several examples here that kind of walk you through some of the things you'll be seeing. Find the line tangent to the curve, and I give it to you, at x equals 1. So you already know the drill on this one, so we have to find a point and we have to find a slope to find the equation of a tangent line. So the first thing is, let's find the derivative. You have to take the derivative of this thing with respect to x. So dy dx is 2. The derivative of the tangent is the secant squared of pi x over 4 times, and then the chain rule, the derivative of the inside, pi over 4. Okay, so there's our derivative. I need to take this derivative and evaluate it when x equals 1. So I want to find the value at 1. So just take this right here and multiply it to the 2, gives me a pi over 2. And then times the secant, plugging in 1 here, will be, this is the secant squared of pi over 4. Okay, the secant of pi over 4, okay, this is a squared, so we look at the squared outside this. So the secant of pi over 4 is the square root of 2. So this becomes pi over 2, the square root of 2 squared, because it's secant squared. And so this whole thing just becomes pi. So my slope is pi. Now, I also need to know the y value. I got to have a point, correct? So that means I have to come up here to this equation to find the point. I only have the x coordinate of the point. I need the y coordinate of the point. So what is y at 1? Looking at y as a function notation. What is y evaluated at 1? And so you simply plug in 1 into this equation. And you'll get pi over 4. The tangent of pi over 4 is 1, so this is 2. So there's my point, there's my slope, and so my tangent line equation is going to be the y value plus the slope times x minus 1, the x coordinate. There is the equation of my tangent line. This is a common practice that you'll be doing. Here's another example. Kind of shows the same thing, only this time my equation was given to me implicitly, so I have to use implicit differentiation for this. Let's find dy dx. So I need to take the derivative of 2x plus, and then I have a chain rule, so I have the first times the derivative of the second plus the second times the derivative of the first, which is 1. Take the derivative of this, which is 2y dy dx, chain rule, equals 0. Okay? And so then we need to solve for dy dx, so we clean all this up, and we can start moving things around. So dy dx plus y minus 2y dy dx equals 0. Everything with the dy dx stays, everything that doesn't goes away, and then the dy dx I'm going to factor out. So I get dy dx times x minus 2y equals negative 2x minus y. And so now I have dy dx. Negative 2x minus y, x minus 2y. So that is my derivative. You can't see it, sorry. There's my derivative. Okay. So now I need to be able to take this. I have to find my slope, and then I also have to find my point. They gave me the point, 2, 3. So I need to find the slope evaluated at this point, 2, 3. So we plug in the 2 and the 3 into this equation. There's the negative 2, there's the 2, minus the 3. Down here is the 2, minus the 2 times the 3. Okay? And then if you work all this out on top, you're going to get a negative 7. You work this out on the bottom, you're going to get negative 4. So this is 7 over 4. So I have my point, I have my slope. Here's my tangent line equation. It is 3 plus 7/4 x minus 2. And there you go. Okay? Let's look at the next one I have. A little bit different than that one. So now let's look at our equation right here. Y equals this. Find any points where the tangent line is horizontal. They like to ask that kind of a question also. Okay? So when you read a question like this, start asking, what does it mean to be horizontal? I got to find the equation of a line. That means I got to find a slope and a point, and horizontal is related to the slope aspect because horizontal lines have a slope of 0. And that's the key to this. Take the derivative with respect to x to help us find slopes. This is a 1/2 out in front. And then we want to find the derivative of this top part, which is e to the x minus e to the negative x. And I want that to be 0 because I have tangent lines that are horizontal. The only way this is going to be equal to 0 is if the stuff in the parentheses is 0, and that allows me to break that out in this fashion. I'm going to change this negative exponent to a positive so you can see this thing as a fraction of 1 over e to the x. And then if I solve this, I can multiply by the LCD, which is e to the x. I get e to the 2x minus 1 equals 0. Move the 1 over, so now I have e to the 2x equals 1. But 1 I can write as e to the 0. That means by our rules that I can take that exponents, and now I know that. And then x must be equal to 0. Okay, so that's not all of it. It says find any point or points. Well, I only have one x, okay? But that's just the x coordinate. I need to find the point, which means I also need the y. So keep an eye out for things like that. Find the points means you need to give me an xy point. All right? So then how do I find the point? Well, I got to plug it back into here. So y is e to the 0 plus e to the 0 divided by 2. And so this 0 is going to be 1 plus 1, which is 2 over 2, which is 1. And then you write your answer, which is you have a horizontal tangent at the point 0, 1. And there's your answer right there. Okay? Lastly, we have this one like this. This is how they like to do some free response questions and stuff. So the first thing I have you do is find the derivative of a curve in that fashion. And so let's find that derivative. Let's find dy dx. So we have a lot going on here. We got a product rule here. We have a product rule here. Look for those in your problems. Product rules are always in parentheses. So here we go. It is the first times the derivative of the second, which is 2y dy dx, plus the second times the derivative of the first, which is 1, minus another product rule. It is the first times the derivative of the second, plus the second times the derivative of the first. And the derivative constant is 0. So there's your derivative right there. Okay? We need to get all the dy dx's on one side, everything else on the other. Start by cleaning this up. Numbers, letters in alphabetical order, dy dx on the end. Y squared. Don't forget to distribute. Negative x to the third dy dx. Negative 3x squared y equals 0. All right, so start moving all that stuff around. Things with dy dx stay, things that without it go to the other side, and factor out dy dx. So dy dx times 2xy minus x to the third equals 3x squared y minus y squared. And so now we have our final answer. X squared y minus y squared, 2xy minus x to the third. Okay, so that is dy dx. Now, once I have that, then I can continue on. So the second part here is it says find an equation for the tangent line, which means we need a point and slope, at each point on the curve with an x-coordinate of 1. Okay, so how do I find these points? Well, I have to go take x equals 1 and find me the y points that go with it. So here's part B. You need to take the 1 and plug it into there for x. So you're going to have y squared minus y equals 6. This is a quadratic that you can then solve by factoring. 0, you got y, 3, 2 minus plus. So y is going to be a 3 or y is going to be a negative 2. Okay, so that means the 2 points you need to look at in our problem is 1, 3 and 1, negative 2. So this tells me I'm going to have 2 different tangent lines. Okay, so that means I got to find the slope of each one. So let's find the slope of this point. So what is the derivative evaluated at the point 1, 3? So then we plug those numbers into here. 3 times 1 squared times 3 minus 3 squared. And down here we'll have 2 times 1 times 3 minus 1 cubed. So the top part here is going to be a 9 minus a 9. So the top part is going to be 0. Down here is a 6 minus 1, which is a 5. So this thing is just 0. And then the next one, what is dy dx evaluated at the point 1, negative 2? So again, plugging it into here gives me 3 times 1 squared times negative 2 minus negative 2 squared. Down here I have 2 times 1 times negative 2 minus 1 cubed. So we need to work this one out. So on top right here is going to be 3 times that is what? Negative 6 minus a 4. Down here I'm going to have a negative 4 minus a 1. So this looks like negative 10 over negative 5, which is simply a 2. So my two tangent lines are these lines. So at the point 1, 3, I'm going to get y equals the y value, 3, okay, and the slope is 0, so it's going to be plus 0 times x minus 1, which is simply y equals 3. At the point 1, negative 2, I got y equals negative 2 plus the slope times x minus a negative, I'm sorry, x minus 1. And so there's my tangent line there. So this is a common thing that they do on the AP exam, so you want to make sure that you can do this one, okay? So the next question is, and the last one, find the x-coordinate of each point, there it is again, on the curve, but I'm only looking for the x-coordinate, where the tangent line is vertical, okay? So let's go and do that. What does it mean for a tangent line to be vertical? I'm going to have to turn my paper over. So to be vertical, I'm rewriting that tangent here. 3x squared y squared, 2xy minus x to the third. For a tangent to be vertical, the slope has to be undefined. So dy dx is undefined when 2xy minus x to the 3 equals 0, because you can't have 0 in the bottom of a fraction. Okay? So then let's figure this out. There's a common factor of x, so we factor out the x. I get 2y minus x squared equal to 0, which means x equals 0, or 2y minus x squared equals 0. What I'm going to do is I'm going to get, there's one answer right there. Okay? I need to look for an answer in this one. So what I'm going to do is I'm going to solve for y. I'm going to add the x squared and divide by 2. So y is x squared divided by 2. Okay? So that's a y value. So I can go back to the original equation, which was this right here. Minus x to the third y equals 6. Take that y value and plug it in. Okay? To find an x coordinate for that y. So that tells me over here I'm going to get x times x squared over 2 squared, x to the third times x squared over 2 equals 6. This squared is x to the fourth times another x is x to the fifth. 2 squared is 4. This times that is x to the fifth divided by 2, and there's a 6. So get rid of the fractions over here. I'm going to multiply everything by 4, so I get x to the fifth minus 2x to the fifth equals 24. This gives me a negative x to the fifth equals 24. And so now I have x to the fifth equals negative 24. So x is the fifth root of a negative 24, which is fine because it's an odd root. So what is my answer? There will be vertical tangents at x equals 0 and x equals the fifth root of a negative 24. And that's how you can do that. Okay? So we'll be doing more of these problems together, but that concludes this video.